All right, we're off. A couple administrative details as we start. As usual, there was not a prep assignment today. So sorry about that. Apparently someone left an apple instead of a nickel today, so if anybody wants an apple, there's one up here. Not sure I would trust leftover food, but we do have some homework due on Friday. A little bit more practice with under dam circuits and filter designs, so kind of just continuing that theme. Hopefully, we're all pretty comfortable with that from yesterday's lab. We'll talk about it a little bit more today. And some other aspects associated with that. That lab will be due Tuesday before our quiz next week. So, general reminder, we have quiz 3 on Tuesday next week. Same setup, probably. I have to reserve the room, make sure it's available, but I assume we'll be in the same location. All the same things. We'll start at 3:15. Give people who are transporting a little bit extra time to get there. So nothing particularly new. We'll include material we talked about today. But largely what we're talking about today is things we discussed before. On a, I guess, slightly related note, I did look at our exam schedule, final exam schedule before class. I suppose I should put this on Brightspace. But I've highlighted where our exam is, so we're on that Monday, May 11th, a little bit over a month from now, 10:30. So it's something we should be planning for as well. Even though you probably don't care right at this moment, the final is cumulative with a concentration on uniform material. Not a topic we really need to go into a lot more detail right now, but something that should be in the back of our mind. That is the second week of finals week. The last day of finals is the 13th. So as you plan your scheduling, think about, I guess, when finals are. This is the only final that's important, of course, but I assume you want to do well in your others. So, other than that, I don't think I have anything else really administrative to say. I will mention, I think I said this on Monday, you get all 3 grid sheets for quiz 3 on Tuesday next week. And I believe I brought this up. In the exam 1 crib sheets, there are op-amp circuits with associated formulas. A little bit more than we talked about in class. We really just looked at the inverting and the non-inverting with a concentration on the non-inverting, because it is the more useful one in terms of filter design. Anybody have any questions on anything? Everybody's good? Guys, change location.
You were blocking the pad, so we didn't want to follow.
You couldn't get through?
Oh, we just didn't move.
I will. It was kind of a funny thing in my perception, though. I don't know, maybe you weren't aware. I don't know who was playing one of my lectures in lab yesterday, but I was listening to myself, and I actually thought I sounded angry. Which it's worth mentioning that I have never gotten angry in class. I mean, I've never gotten really angry with any student. I've gotten frustrated, but I'll admit I've gotten frustrated with questions in class, especially if, like, I spent 5 minutes talking about something and then someone asked me something I just covered in a lot of detail. That's a little frustrating if you mean someone's not paying attention. And I have twice in my life asked a student to leave my office because our conversation was just not going well. But I was never mad. So if I sound mad in the videos or if I sound mad in class, I am not mad. That's worth sharing. I'm not an angry instructor. I'm not. Well, until we start talking about politics, then I get to be an angry person. But we're not going to do that in class. So that's not going to happen. But that aside, I don't know. Has anybody else thought I sounded angry? No? All right. That's good. I sounded angry to myself, but it's one reason. I don't know if anybody's ever recorded themselves and listened to themselves talk. It's an awful experience. Like I hate this. That's not what I sound like. So there's probably value in doing that, but I don't like to. So, all right. back to our regularly scheduled programming. It was worth discussing that. We're going to talk about this. I'm going to give you an opportunity to do this as well, but I want to talk about a couple things first. Here's our design goal. So we're designing essentially a bandpass filter with frequencies in this range. I know you did some of this in class yesterday or in lab yesterday, and we looked at it before, but I want to elaborate on some characterizations with this. If we're doing a bandpass filter with an RLC series circuit, as indicated in the top, in our spec here, number one, I suppose, where's our output? Where's our output? Yeah. So across the capacitor gives us what type of filter? Low pass. So capacitor is a low pass filter. This is a band pass.
Oh,
So maybe I should make it larger. Yeah.
yeah, what's the resistor?
Across the resistor. Oops, sorry, I keep opening my iPod case in my pocket. Something you shouldn't do is stick your hands in your pocket and fiddle with stuff. It's not good teaching style, but I do it a lot. Not good discussion style. So anyway, yes, bandpass filter, we're going to measure across our resistor. To point out here, we're looking at item C. If our stop bands are 20 dB, and we can draw this out, and I've asked you to do this as part of your exercises, but we can set this up. So our frequency range 10 to 3, 10 to 5. What's our interpretation there? So make a little note of what we just said. Bandpass. V out across the resistor. If the frequency range is 10 to the 3, 10 to the 5, what's our interpretation? What must be at 10 to the 3? What must be at 10 to the 5 radians per second? In terms of math characteristics, I suppose. Yeah, they have to be poles. So our cutoff frequency, we have 2, omega C low, 10 to the 3, and that's a pole. That has to be a pole. Omega C high, 10 to the 5, that's a pole. I want to be a little bit more specific though. It's a pole. Well, what order of pole is it? Single, double, triple? And what we look at here is the change in slope. So if we were to plot this as part of the spec, I said our roll-off is kind of an absolute value interpretation of slope. So if it's a high pass filter plus 20 dB per decade is our slope. If it's a low pass filter, minus 20 dB per decade, but we can call that roll-off and just call it 20 dB per decade. But just kind of a little terminology there. So we can go grab some Bodhi paper and just pick up this comment after doing the plot. So I'm not going to give us units on the y-axis just yet. There's 10 to the 3. There's 10 to the 5. There's some pass band. And we do know this slope is plus 20 dB per decade. And this slope minus 20 dB per decade. So that said, when I look at this pole, I know there's a pole here, and I know there's a pole here. What order of pole does this have to be? First, second, third? Does have to be a first. Why? How do we know it's a first order pole? Yeah. Are you gonna answer? No, just okay. How do we know it's a first order pole? Because when we cross a pole, the change in slope tells us the order. So we went from plus 20 dB per decade to effectively 0 dB per decade. It's a change of minus 20. So the slope changes by that factor. So we can write that down. It's probably not a bad thing to have in our notes. When we cross a pole, Oops. The change in slope tells us the size of the pole. Double, triple. This is true for zero as well. Single, double, etc. For each change of minus 20n, so then n, I should be more specific, minus 20n dB per decade for each change of just 20 dB per decade. N changes is an n pole. E.g., for example, slope changes by minus 60 dB per decade, and changes is the key word here. Then it's a triple pole. Minus 60 equals minus 20n, n equals 3. Triple pole. I don't know if I worded that as beautifully as I could, but concept I hope is there. Same thing as for zeros. If we cross a zero and the slope changes by plus 20n, then n is the order of our zero. So we do have a single pole here. Two single poles, and that tells us what our transfer function would be. So we can go back and say h of s is something along the lines of s plus 10 to the 3 times s plus 10 to the 5 in our denominator. I can point out, we've done this already, the generic transfer function for the output across the resistor is R over LS over S squared plus R over LS plus 1 over LC. So I had you do that in class yesterday. This is in your notes already. Consider this a solved problem and just use previous work. Yeah. Did I say hertz? I didn't put units. What did I say in the problem? Yeah. Let's just make it easier because I don't feel like doing the conversion. So it was a good point. Normally, I would use radians per second just to make it easier to plot. As was asked, if it was hertz, then we have to multiply everything by 2 pi, and that's going to change our numbers a bit. So just to make life a little bit easier. As we saw in the lab, LT Spice, the equipment, the Scopy, everything is in hertz. So we do have to make that conversion essentially as we're looking at our equipment, but doing math stuff, it's a little bit faster just to use radians per second. But thanks for noticing that. So anyway, here's our generic expression. We can write out our mathematics a little bit, do the multiplication out, and this winds up being s squared plus 1 0 1 0 0 one more 0 s plus 10 to the 8th. And because of the form, here is R over L, and there's 1 over LC.
Wait. I can't.
Which one?
No, the middle term.
101,000.
Oh.
So 101,000. So I mean, just by doing the math out, it's 10 to the 5 plus 10 to the 3. I realize my handwriting may be not so pretty, but still. So that said, we do know what the numerator is, even though it's not, oops, missing a zero. It's only relevant in terms of the fact that we're doing down past filter. So we can write that out. But we've set up our denominator, and based on previous experience, our denominator tells us what our R, L, and C values would be with having to make some choice. There is a little bit more information. In the specified frequency range, the gain must be 20 dB. So I could go back to my plot and say this, if I zoom in here, is 20, and then 0, that's units dB, minus 20, etc., minus 40. So there's our plot. Ultimately, though, we do have to translate gain to a circuit. And so we've had some practice with that, talked about it a bit in class. We know in order to get that gain, we can translate back 20 dB equals 20 log of some A term. There is our passband gain. And how do we get a passband gain? Something larger than 0. How do we do that? What's the only thing that's going to give us larger than 0? I'm not talking about underdamped. It's the only thing that's going to give us a passband larger than 0. Yeah. Well, what's circuit? So we need a circuit stage. What's that?
Like a circuit can
An op-amp circuit. We need an op-amp circuit to give us a passband gain. So here's our passband gain. We can do the math. Remember to translate. We could write A equals 10 to the dB value over 20, and we can plug in there 10 to the 20 over 20, and that winds up being 10 to the 1, of course. And we have a passband gain of 10. And usually, since it's voltage amplifier, it is unitless, but we often say volts per volt, just to indicate a voltage amplifier. So volts per volt cancels to 1, but we use units, volts per volt. So this is our amplifier gain. And our amplifier gain essentially goes back in our transfer function out front. You put a little A there to indicate we haven't done amplifier gain yet, but that finishes out our math for determining the transfer.
Can you explain how you got the 10 again?
So I looked at my passband gain, and my passband, here's my gain, 20 dB passband gain. But I have to translate dB back to some circuit parameter. I mean, what we're saying here is the magnitude of the transfer function in this range of 10 to the 3 to 10 to the 5 is 20 dB. And magnitude of the transfer function, I mean, kind of going back a little bit more deeply than what we've done before. Magnitude of transfer function, 20 log magnitude of h of j omega in that range equals 20 dB for 10 to the 3 less than omega less than 10 to the 5. So this is the reverse of what we did when we're plotting our Bode plots. If the transfer function is constant, what do we do in that range? 20 log of that value. Well, now we know that value and we're asking, what's the constant? We're just going the other way. Does that make sense? So going backwards instead of forward. And I just solved this, of course. We know log of h of j omega has to be 1. 20 times 1 is 20. Or we could go the other way, knowing the dB value and using this generic way. all that said, we can put our pieces together. Our transfer function, h of s. There's our gain, 101,000 s. Just to write it out again, s squared plus 101,000 s plus 10 to the 8th. Well, here's our gain, amplifier gain. Here's our R over L. And here's our 1 over LC. Well, our circuit is going to look like this. Not that. Inductor, capacitor, and our output across the resistor. Something to point out, and I saw this a few times yesterday, when we feed into the amplifier circuit, this orientation gives us the output across the resistor as the input to our amplifier stage. Multi-stage circuit, output of one stage, input to the next stage. Continuing, output of the next stage, input to the next stage, et cetera, et cetera. When we talk about output, we talk about this node relative to ground. This node is our input to our op-amp circuit. We're going to use a not inverting like we did before. And we can do this quickly. This has a gain of 10. You can pick any values you want. I like to use reasonable values in terms of things that we're more likely to be working with. So 9K and 1K, the gain 1 plus R2 over R1, 1 over 9 over 1 is 10. Seen that a number of times before, doesn't hurt to rehash it. 1 over LC, 10 to the 8th. I often will pick 10 to the minus 7 for C, and L is 0.1. So not necessarily common values. Let's skip some of the math to set that up. I mean, this is an inductor that we worked with in class. That said, that inductor does have a problem. What was the problem with our inductors again?
Resistance.
Resistive. And we saw that in the lab. It was due yesterday, so around the 4th. That did change our experimental results as opposed to oops, wrong one.
We didn't measure circuit.
Last week. The lab was due yesterday. Lab 4 was due yesterday. And so our final characteristic here, we're not working with alpha and omega because we work directly with the transfer function. We have R over L equals 101,000. And we can get R equals, having already picked a value for L, times 0.1. And we get 10.1 kiloohms. And we're done. So here's the design for our bandpass filter using a second order RLC circuit with the output across the resistor. There's something that's not great about this. I mean, one thing, I'm going to have you do the work. And before I dive into that, I want us to think about other ways to design this. If I take this circuit or this filter response and just look at that, what do we see? What would you call that? It's a high pass filter. If I just look at that, what's that? Low pass filter. So we can always make a band pass filter by cascading low pass and high pass filters. So there's an important comment. We can always make a band pass filter by making a low pass filter and then making a high pass filter and doing it in multi-stage circuit. What's fundamentally kind of not good about this particular circuit? Yeah. Yeah, 20 dB is not a great stop band. So if I gave you the exercise, and I did give you this in the homework, so I'm kind of setting the stage for you to get ahead there. What do we want to do if the expectation is 40 dB here and 40 dB here? How are we going to build that? Yeah. So double poles are not quite. I mean, we got to be careful. We do need a double pole, but I want to be a little bit more specific. Yeah.
Another normal LC circuit.
another RLC circuit, but again, 40 dB and 40 dB. So how do I get 40 dB if I think of just a low pass filter? And so before you answer, 1 second, I do want to point out we can't do this same RLC circuit with the output across the resistor cascade. Why can we not do that? And we could, but we wouldn't really be meeting spec. What's the problem with that? What haven't I drawn here in the circuit? The corrections. What are my corrections here and here for this circuit? They're both -3. They both meet spec. -3 is the definition, single pole. If I cascade another RLC circuit output across the resistor, what do I wind up having here? -6 correction because I have a double pole. And I have no longer met spec because my cutoff frequency is not 10 to the 3 and 10 to the 5 because my correction is -6. So what do we do instead? As I was just kind of going to, what do we build to give us our 40? Second order circuit. And what sort of second order circuit is going to give us this part? We're going to build a high pass filter with a resonant frequency of 10 to the 3. We're going to build a low pass filter with a resonant frequency of 10 to the 5. That's how we get a circuit that meets that. Both of those, when I say resonant frequency, both of those RLC circuits are underdamped circuits. And underdamped with a correction of -3.
Do our RLC circuits like this one doesn't have a slope of minus or plus 40 dB. Usually I thought RLC has
The-
40.
So if the transition from low pass or high pass, if we're doing output across the inductor, output across the capacitor, then we have a change of 40 dB at the resonant frequency underdamped. If it's overdamped, then we just go through the math like we've done before. And this is, I should point out, didn't explicitly say that, this is an overdamped response. We will look at the underdamped response. It won't be part of your task, but we'll talk about it in class because it is an important circuit. That said, I do want you to just practice quickly. It's kind of a pick up on what you did yesterday in the lab. So if I want to do this circuit with just first order circuits, same specs, how do you build it? And so consider this kind of a practice test problem. Same specs, use first order circuits. First order circuits are real poles always. And how do we do it? We already answered the question, low pass filter and high pass filter. So this is an exercise for you. It's kind of picking up what we did in the lab, but backing up a step and letting you do it a little bit more yourself.
Exact same circuit, or are we doing the?
Is it? Oh, well, you're not doing an RLC circuit. You're doing first order circuits only. First order circuits only. Yeah.
Are we gonna still keep it megahertz then, or are we gonna be?
Oh, yeah, radians per second. Thanks. Radians per second. Let's make our life a little bit easier. Oops. So again, see a lot of you seem to be looking. Where's my? To get this, what can we build? A high pass filter with a cutoff frequency of what? So any high pass filter, how can we build a first order high pass filter? First order high pass filter. There's two choices. And inductor and resistor output across the inductor.
And it's just kind of third. If it's only first order, it's like if it's only first order, it's not like in between. Like the stop band is like any frequency.
Oh, there's no question. First order, we get a single pole. And where's that pole gonna be?
That will be
It's gonna be a 10 to the 3. High pass filter, ignoring this, here's our pole. Our pole is our cutoff frequency.
like I got confused because you're also mentioning 10 to the fifth.
Well, but overall, we're building a band pass filter. How do I get this part?
Low pass.
Low pass filter. So I need a high pass filter and a low pass filter. I also need something that's giving me the pass band gain, but we've already solved that. We already know what that is. So, I mean, the first thing to do is, what is your circuit going to look like? There's choices here. What's my circuit going to look like? I don't need numbers. What does it just look like? I need three things. I need a low pass filter with a cutoff frequency of what?
10 cube.
Not 10 cube, the low pass filter. 10 to the 5th. I need a high pass filter with a cutoff frequency of what?
No, that's
10 to the 3 radians per second. And I need a gain of what? We've already done that. Pass band gain. Which corresponds to 10 or more. We've already done that math, taking advantage of previous work. How do I build this circuit? We already know it's an op-amp circuit. We've done that. How do I build this circuit? You have two choices. We already discussed. It's either an RL circuit or an RC circuit. If it's an RL circuit, where's our output? Inductor. If it's an RC circuit, where's our output? Not the capacitor, the resistor. How about, I did that backwards, sorry, I was talking about. No. I did that, sorry. Low pass filter, RL or LC, we can do both. Low pass filter, output across the capacitor, RL circuit, output across resistor. We can draw the circuit, we can get partial credit. That's what you need, identifying what you need, sketching the circuit, then you go figure out the numbers. But you want to make sure you sketch out the circuit so you know what you're working.
From the left, you start with high pass, right?
It doesn't matter. You can do either order. It's multiplication. Is there a difference in 2 times 3 versus 3 times 2? So multiplication, any order. So we're doing low pass filter times gain times high pass filter, or high pass filter times gain times low pass filter, whatever we want. Low pass filter times voltage follower times high pass filter times voltage follower times gain. I mean, that's needlessly complex, but. Good. Now you just gotta figure out your value. Oh, yeah, you're almost done. The 1 over C is your pole, right? Right. We don't want to already. You don't need second order circuits here. It should be first order circuit. Because that was part of the spec that we put away. Second order circuits give you a better stop end, so ultimately you might want that. But it's not part of the design process here. Does that make sense?
Yeah.
You get a lot of people missing for week before the test. Yeah, trying to get. Oh. Wow. What's this? Go ahead, do that. That's for them.
I did it, because I was stage one with the content. Stage three, and also that's so soon. Or when.
They don't need second order circuits, you know. So the first one should, this one should use that. Because second order, I mean, that was part of the spec, it's both circuits should be first order. All we're trying to do is change the slope by 20 dB. Second order changes the slope to 40. What's that? So which circuit is which?
This is the high pass filter.
Okay. So our high pass filter should have a cutoff frequency of what?
But then
Which part of the plot is our high pass filter? Here's our plot. Is that the high pass or the low? Oops.
That is the high.
So what's my cutoff frequency for that?
Is above 3.
Right. And what's that? High pass or low pass? And what's my cutoff frequency? See what I'm saying? Okay.
But 1 over RC will give us the cutoff.
For first order circuits, our pole, which is the cutoff frequency, is 1 over RC for an RC circuit. Yes, always. Doesn't matter high pass or low pass. Both 1 over RC. Because our transfer function for the low pass is 1 over RC over S plus 1 over RC. So denominator is S plus 1 over RC. There's our pole. Transfer function for high pass, S over S plus 1 over RC. Same denominator. Same pole, but because the numerator is different filter.
And for inductor and resistor, it's R over L.
Yeah.
Yeah.
The three. This is all I'm looking for.
So this transfer function, this circuit doesn't have this transfer.
This is.
So it's EL over ZL plus DL.
Well, that's just like.
Your numerator. Yes.
This high pass is my. I'm doing the. Oh, yes.
Oh, yeah, it's like I tried to set, yeah, because then I got.
Yeah.
It was. C, or I'm sorry, no. Over. And then. Right.
Not quite. Well, there's two things, so, right, our starting page is not right. But remember, when you cross the pole, how does the phase change? Across a pole, phase changes by negative 90. And also, when you go to high frequencies, when you get away from that change, phase clock becomes constant.
No, yeah, I was gonna point out, yeah.
Non-inverting is better because the inverting can actually change the transfer function. Because what's true when we look at our non-inverting, like when I drew this. Wherever. What's true about the current on this path here? What was we had two op-amp rules. Remember what one of them was in terms of current?
Like.
No. Does anybody remember our op-amp rule for current? They both equal zero. No current into the input of an op-amp. So this current is zero, which means the current here is what relative to here? So when I do PCL, so if I have current coming here, where does it have to go? It has to go down. So the current here and the current here are the same, which means these are in series. If I put a an inverting here, I have a resistor on this path. And then all of a sudden this and this are not in series. We had drawn that once before, but so in general, this is why non-inverting is a better choice in cascaded circuit. I was talking to Dr. Eisen yesterday about filters, and he never did analog circuits as filters.
Yeah.
All done visually now. So, and you'll get that in signals. Have some discussion, probably have some discussion about filters today. But if you want to be an old stereo person, yeah, people still use vacuum tubes and stuff like that. Anybody in the old stereo equipment? I think I've asked this before. No one? Who has a circuit for me? Who wants to share? Yeah.
Resistor and
Okay.
Since that stage of circuit is at a occupancy of 10, they're.
So what values?
So then and still get down there, get 0.1.
Okay.
The second stage, that's just op amp. Yeah, I'm pretty sure. So yeah, two resistors.
And you use the values we did before?
Yep. All right, last stage is RC.
C or R first?
R. Like there, capacitors.
And there's V out. And what are our values?
It's kind of negative that. I haven't got that part.
Anybody do this circuit and values for R and C? Yeah. 1 to the 8th. 10 to the minus 8. Gain. High pass filter. Omega C equals 10 to the 3rd radians per second. Low pass filter. There are an infinite number of possibilities. So, I mean, it's usually better to design something that has realistic values. This circuit certainly has realistic values. But on paper, we can do whatever we want. So everyone agree? That said, I want to go back to our transfer function. We had sketched this out based on our information. We could have got it from the circuit as well, but I do want to include the phase plot. So adding the other numbers, 0, 90 degrees, 180, minus 90 degrees, minus 180. Here was our transfer function. What's my low frequency phase? You can kind of do this by inspection. We can always dive in with the math, but we can do it by inspection a little bit. We didn't write this out. We know what our poles are that was given to us up here. We already determined this. Poles, 10 to the 3, 10 to the 5. What are my zeros? And I do have zeros. I have a 0 at 0. What's my starting low frequency phase? 90. Why 90? Because we have a 0 at 0. If we have a 0 at 0, our low frequency phase is 90. We can always dive in, let them make it go to 0, look at our transfer function, do the phasor stuff. But that's a little bit more work. As we recognize 0 at 0, our low frequency phase is 90. We have a pole at 10 to the 3, pole at 10 to the 5. When do we start making our change in phase? As we cross the pole 1 decade prior to the pole. So because we have a pole at 10 to the 3, we're going to make single pole at 10 to the 3, phase change of minus 90 degrees. We're going to start that at 10 to the 2 and end that at 10 to the 4. There's the phase change due to our pole at 10 to the 3. We do the same thing for our pole at 10 to the 5. In this case, it looks like we continue a slope. It is not a slope. It's a change in value. We need to be careful. And then what do I do past 10 to the 6? It's a flat line, so to speak. It's straight. The phase stays at minus 90 degrees per decade. We draw past to indicate that. So the reason I did this is ultimately, frequently, I should say, we are given this information. And the question, the unit 2 question is, if my input is something, what's my output? And if I know this, we don't have to do any of the complex math from unit 2. So I've done that, and I'm going to let you practice it. I'm going to do one problem. I'm going to let you do more than one. Here, somewhere, is a VN. So there's a VN. Let's make life easy and just insert that. Oops. I don't want a vertical one. I want a landscape. Come on. So, what's the very first piece of information we need out of this equation? Starting point. What do we need to know first before anything else? Not yet. So,
Phase,
not yet.
cutoff frequency.
No, it's an equation. There is no cutoff frequency. This is our input. It's the very first thing we have to know. Yeah.
Well,
Oh, we're trying to find V out. So we have a V in, here's our V in, we're trying to find V out. What's the very first piece of information we need to look at?
frequency.
The frequency. We need to know what frequency we're talking about. Here's our frequency. So we are saying at 1,000 radians per second. We can write this in phasor form. Oops. as Vn equals 0.5 angle 45 degrees, which is at 1,000 radians per second. There's our phasor form at 1,000 radians per second. Why is 1,000 radians per second important? Because V out in phasor form is magnitude of h of j omega times angle of h of j omega times Vn, which we already know in phasor form. But magnitude of h of j omega, in order to find that, we need to know what frequency we're talking about. So at 1,000 radians per second, what do? We go look at our plot. Here is 1,000 radians per second. What is our value at 1,000 radians per second? So on the plot, it's 20 dB, but I'm going to include the correction. So it's actually 17. So it's a fine answer. I didn't write the correction down, but there's the information we care about. So we'll erase that and come back to it. Come on, you. At 1,000 radians per second. You're not fitting on page. Magnitude of, or our dB value, I should say. It's not quite magnitude yet. dB value is 17 dB. We need to translate that into magnitude of h of j omega, and we use that. I could be a little bit more specific and say magnitude of j 1,000, because that's our omega value, equals 20 log, or 20 to the dB value. Let's write that correctly, not incorrectly. 10 to the dB value over 20, going from dB back to value. We've written that equation before. If we do that out, it's 7.07. And likewise, we can look at our angle, VH, we just go straight off the plot. Here, we don't even have to do any work. At 1,000 radians per second, what's my angle? It's positive 45 degrees, plus 45 degrees. Do we all agree? Again, we're just reading off the plot, so straight up. So all that said, we wind up with 7.07 angle 45 degrees. There's our transfer function in phasor form times 0.5 angle 45 degrees. We do that math out, that's 3.53 angle 90 degrees, roughly. Ultimately, we want to translate that back to that. Maybe I can lift this up, keep it all on the same page, so I don't have to go to the next page. V out as a function of time. Well, there's our amplitude. This is all just unit 2 stuff. 3.53 sine. What's my frequency? Output frequency has to be the same as input frequency. We don't have anything that's frequency shifting. Those things do exist, just not in our circuits. This is a linear circuit. Plus 90 degrees in units volts. There's our process. So identify the dB value, translate it back to some number, our magnitude value. Identify the phase value. I mean, that's easy. We don't have to do anything other than read it off the plot. Do the phasor math out, multiplication for our magnitudes, addition for our phases, and go back to our time domain form. So I have a little bit of practice for you. So the same plot. to make that larger, figure out the outputs. Yeah.
The work would previously did, like, before we had the second order circuit that had a slope of 20 dB. And now with the same thing, it still has a slope of 20 dB because it's the first order circuit, and you can't have more than 20 dB with first order.
So,
Then why we did it,
I mean, why did we do it?
because the slope didn't change.
I didn't have you, I mean, in the homework, I'm having you do steeper slope.
And here it was just.
I mean, yeah, just practice. That's why we underdamp a second order circuit. So when we do the higher slopes, we need to underdamp. So we can make the correction -3 as opposed to -6. In the past, man, the dB value is 20, right? So the 17 came from the correction. Yes, yeah. Good.
You said the op-amp obviously has no current goes to it. Do they like make it introduce extra current into it?
Oh, why does that happen? Because, I mean, this is a whole conversation we'll do in electronics, but. The input circuit for the op-amp is what's called a high impedance input. And so high impedance just means really big resistor. So in reality, for the op-amp I use in electronics, I deliberately use that, it does have a tiny bit of current going. There are much better op-amps that have, the current is really small, 10 to the -12, so 10 to the -14 or something. So it is not an unreasonable expectation. And as usual, I'm only telling you a fraction of the story, because there are more complicated things when you look at. What happens when the voltage changes and things like that. And so there's a reason we say impedance. In class, I usually do resistance, which is easier. Impedance is vectors and capacitors, usually capacitors. More complicated. There is much more to the story than I tell you.
How do we do that?
And so once you finish this, feel free to upload. The grade scope should be set up for today.
Yeah, except for like the correct.
Oh. If anybody needs the phase plot. Here's the phase plot. I'll leave it up for a minute and I'll put it back.
Oh. And then you go back to yeah. And this is why I should start using the other one, the other different spots, because now I am literally trying to assume what they.
It's what, give us something. First.
I got it. Well, I think I got 5. Like I don't even see. I need to start using those ones. And you, I can't, I really can't, because look at where I'm supposed to pay the. Like. I don't even know which way.
Equals zero, so you cancel out.
Oh, for this.
That's all that is. And zero, zero plus 45.
And now this is where I'm going to the whole.
So the empty.
No, that's the best parts.
Yeah.
Part of the trade.
What's that? So what's the dB value?
Up the voltage.
I'm just gonna say.
What's our, where's 10 to the 4?
I'll be at
100 magnitude. Yeah.
So HFS at like the.
Well, what was it in the plot? So you didn't do your y-axis, but
Or, sorry. It would be zero. It's zero.
what's the dB value at 10 to the 4? What's that? 20, yeah.
Yes, because I can't see it on mine, so I'm like, where you go? Yeah, I'm going for it. No, that's the.
Or log, log, you mean 20 times log?
Oh,
Oh, log of 10 is log.
yeah. So I'm
Yeah.
seeing you're trying to.
Yeah.
Does that make sense? Dude, that make sense?
Here, right?
Plus 3 weeks, you see.
So one angle 9.
Yeah, I was saying, I don't even know. Who's gonna shoot it? Yeah. But it could get one of the eight. What's on the back? Oh, wait, well, I had said eight. I thought it's this. Yeah, into the two. See, and then why I can't do. Like, maybe there's.
Oh, no.
I'm gonna just like.
There's one, sorry.
So,
So. So if we bring it back up.
Yeah, that's, well, I guess for the phase, it would just be.
I didn't actually look at your first one, so I should be careful. At 10 to the 2, what's my dB value? 0. So. And 10 to the 0 is anything to the 0. What?
Oh, yeah, I already got it. So would it be?
Does that make sense?
0.5.
So that.
But if you get 0.5.
So one thing, there's a reason I gave you 10 to the 8th. What's the dB value? So this is the third one. At 10 to the 8th, what's my dB value? Well, this slope continues. Negative 40, right? Because 20 dB per decade, negative 20 dB per decade. So at 10 to the 7 minus 20, 10 to the 8 minus 40. Does that make sense? Yeah.
Yeah. Wait.
So is this gonna be on the exam?
Reading the Bodie plots?
Yeah,
Absolutely. Yeah. So for the middle one, just to check, anybody have an answer for me? What's my amplitude?
Two.
I agree, 2. What's my phase? There's a good check in units volts. Everybody agree? Everybody has finished this? All right. So again, if you're done, by all means, take your picture. I'm gonna do a little bit more. So that's it for your job this class. I am gonna look at this. This is from a test. I pulled this from, I think, a year ago. And the question is, what's the transfer function? So I'm given this Bodie plot, straight line approximation. I didn't include any corrections. What's the transfer function? What do we recognize? What do we need to know to get the transfer function? What information do we need? Poles and zeros. We need the poles and the zeros. So what do I have? What are my poles and zeros? Where do I have a pole? Where do I have a zero? Yeah.
0 at 1 and then 4 at 3.
Well, so let's be careful. So this is the magnitude plot. What can I say about the slope here? It just continues going down. So this, it is 1, but it's not a pole or a zero. I mean, it's just, this is MATLAB, so I can't draw that past the edge of the boundary. Just a second, Mr. Durant. So technically, this keeps going like that. So the fact that, oops, not curved, but straight. And I could have made it blue. But yeah, so Mr. Urena.
Let's say we have a 0 at 2 and a pole at 4.
So how does the slope change? So here, what's my slope?
More positive.
It's positive, and if you can read the axis, anybody recognize or read it? What is my slope? Not positive 20. Plus 40 dB per decade. What's my slope here? Minus 20 dB per decade. When I cross 10 to the 2, how does my slope change? Yeah. You gotta be a little bit more specific. Minus 60. The slope is going from plus 40 to minus 20. It's a change of minus 60, which means what? It's a pole or a zero. It's gotta be a pole. The slope is changing in a negative way. It's changing by negative 60, which means what size pole is it? Triple pole. So this is a triple pole. Triple pole. And so going to our transfer function, we can do s plus 10 to the 2. We may have more, so I'll leave that. Cubed. There's a triple pole. We can write that down quickly. What else do we see in our circuit? In our magnitude plot? Yeah. 0 at 40. A 0 at 40. How do I know it's a 0 at 10 to the 4? I said 40, I meant to say 10 to the 4. How do we know it's a 0? I'm going to answer myself. So we're going from minus 20 to 0, so the slope is changing by plus 20 dB per decade. Plus 20. Plus means it's a 0, and it's just 20, so it's a single 0. So this is a single 0, and we can put that in the numerator, s plus 10 to the 4. Do I have any other information about poles and zeros? And the hint is yes, I do. There's one more piece, sure.
0 and 0.
Or not quite, you're close. So,
Negative.
well, but it's not as, it's a 0, but we need to be a little bit more specific. It's a double 0, 0. How do I know it's a double 0? Because my slope is plus 40 dB per decade, going off to minus infinity. And so to get plus 40 dB per decade as a starting slope, I need an S squared term in my numerator, a double zero at zero. You can go back and reference our notes from before. We've talked about that before. This slope, kind of call it starting slope of plus 40 dB per decade, that's a double zero at zero. So we have an S squared term in there. And we can go check a little bit. We can do the limit. So I'm going to add one more thing. I didn't need the extra part of my fraction line. We got enough. But there is something that's missing, and that's a K term. There could be a constant term that we haven't paid attention to. So poles and zeros, that only gives us our parentheses and our S squared in the numerator. It doesn't tell us what the constant would be in our equation. How do we look at that constant? What is the dB value in the limit as omega goes to infinity? Well, we can keep all the dominant terms. We have S squared, S over S cubed times K. These, of course, all cancel, and we get K. In this case, it's relatively easy. Everybody agree with what I wrote? But our value at high frequencies is 0 dB. 20 log of what gives us 0 dB? 1. K in this case is 1. So if I had forgotten to look for this, I would have still gotten full credit because my equation would be correct. But this becomes 1. But if this was 20 dB, it'd be 10 or whatever. So we do have to look for a constant term. So slope or poles and zeros don't give us that constant. Questions? All right, I want to come back, kind of looping back to where we started the class. Here was our bandpass filter from an RLC circuit. I mentioned this before. In order to get this, this is an overdamped circuit. So here's our bandpass. An RLC overdamped circuit response. We can go look at the numbers. We had 10.1 K, 0.1, 10 to the minus 7. Here's our V out across our resistor, R, L, and C. We can look at omega naught, crunch the numbers there, we get 10 to the 4. Alpha is 1/2, 10.1 times 10 to the 3 over 0.1, and we get 50500. This is 10,000. Alpha larger than omega naught, overdamped. That was very quick. We've done this before. If you're not sure, we can talk about it later. What? Proving it's overdamped. That was the circuit we designed. Just checking the numbers. Told you it was overdamped. We had 2 real poles, so we know it's overdamped anyway. What if, instead, I do something like $2,000? And 0.1 and 10 to the minus 7. If I crunch the numbers here, I get alpha is 10,000. And omega naught, still 10,000. This is critically damped, which means we have a double pole at 10,000. Question becomes, and I inadvertently gave you this as a homework problem, and many of you plotted something that was reasonable. How do we plot that? So it's still a bandpass filter. our outputs across our resistor. So bandpass characteristics, critically down. We have no passband to speak of. So if we go through the math, there's 0 dB, there's minus 20, there's minus 40, here's 10 to the 3, a double pole. And we've proved this before, it's been a while, I don't expect you to remember. But at the resonant frequency itself, our dB value is 0 dB. That's an actual value. So for this circuit, that's the actual value. 0 dB at omega naught, actual value. But with that in mind, if I'm drawing the critically damped case relative to the straight line approximation, double pole, what's my correction? -6 for a double pole, right? So straight line approximation, if this is the actual value, then my straight line approximation has to be up here at +6. And what's a little bit tricky is it's a bandpass filter. So my slope is still going to be plus 20 dB on that side, minus 20 dB on that side. Bandpass filter, we have this slope on either side. There's my straight line approximation. I can take this a little bit further and say, all right, let's change this up and say, same circuit. We'll do this quickly. And we'll change that resistor value to be even smaller. We'll make it 100, 0.1, 10 to the minus 7. Omega naught, still 10 to the 4. Alpha now 500. Significantly less. We are now underdamped. And we can look at our damping ratio, and our damping ratio, alpha over omega naught, 0.05. 500 over 10 to the 4, 0.05. Quick math. Not a big deal. That said, I can go look and say, here, for this circuit, we had R was 2000. For this circuit, we're going to say R is 100. And I'm going to start, here's my resonant frequency, 10 to the 3. That's omega naught. Here is 0 dB once again. And there's my actual value. But my correction, I can go look at, my correction is 20 log 1 over 2 times the damping ratio. So it's underdamped, correction at omega naught. Log 1 over 2 times 0.05. And if we do that out, that's 20 dB. That's my, and I can add plus 20. It's plus 20. That's my correction relative to the straight line approximation. But once again, we know that at the resonant frequency, the actual value is 0 dB. What does that mean for us? With my correction being 20 dB, it means my straight line approximation is down here at minus 20 dB, the corresponding point, and we still look at 20 dB per decade as our slopes. Why are you not snapping? Finishing up relatively quickly. I can do this in the last 30 seconds. There's my straight line approximation. Normally I give you a little bit more rules, but I'm just demoing this, not on the past, but it's something that's worth noting. Actual value, straight line approximation. As we are far away from poles and zeros, straight line approximation is always valid. close to the pole and zero. We do some sort of fitting. Here is our actual body plot. You can go simulate this. There's my actual DB body plot, the red dashed line, and then conversion and an asymptote to my green line. What is this? This is a narrow bandpass filter. If you want to tune in at just a given frequency, this is what you built. This is very real, historically. And so strongly underdamped, narrow bandpass filters, voltage across the resistor, but strongly underdamped. Went from that wide pass band, then to the whatever it was, 10 to 10.5, to something very narrow located at 10. And we can underdamp more, move this down more, this gets narrower and narrower. In some ways, it's like old tuners work. You guys owed me about 10 minutes anyway.
Yeah.